we want to discuss differentiation. Okay, so differentiation involves finding the gradient of a curve at a point. Okay, and it is denoted by dx if it is a function of x. Okay, so we want to find the derivative of a function f of x. Then we have this symbol representing that. Okay, so other symbols that we use is f prime of x. Okay, or if the function is denoted by y, then we have y prime. Okay, so here now, if the function is written in terms of y, maybe y equals to f of x now. Okay, so we just say that we are looking for dy dx. Okay, so instead of putting the bracket, we just do away with the brackets and then we have this. Okay, if you want to write f of x there, you can as well write it as d dx of that function f of x. All together. Okay, so what I mean is that anything can be here. The symbol for derivative is just d dx. Okay, so if that function is denoted by y, that's when we now write dy dx. So if it is denoted by f of x, then you have d dx of f of x. And we can write that function directly. Okay, what I mean is, for example, if you have that y equals to x squared, you can, and you want to find derivative, you can say that you are looking for d dx of x squared. You understand now? So once you see this symbol, it means that you find the derivative. So it's clear. Okay. Now, and since it is y as well here, if you write find y prime, so it means that you should find the derivative. All right. So yeah, it's the derivative. Yes, it's a symbol for finding the first derivative. Now, if we begin to, by the time we get to higher derivative now, you will see that we begin to increase the number of primes. So if we have two primes there, if we have two primes, y prime prime, it means that you differentiate twice. Okay, differentiate the first time, the result of the first derivative, you not differentiate again. So that's the meaning of y prime prime. You can as well have f of f prime prime of x. Okay, it means that you differentiate twice. Yeah. So by the time we get to higher derivative, you're going to say that. So now, the gradient of a curve at a point, which we call the instantaneous derivative or instantaneous change, you understand now, is denoted by a very simple formula that is linked to the limits. Okay, so we define the y dx as the limit of f of x plus change in x minus f of x divided by change in x, as change in x tends to 0. Okay, some people prefer to use h instead of change in x. Okay, they can write it this way: the limit of f of x plus h representing that change in x, okay, minus f of x over h, as h tends to 0. Okay. Now, some people also define it in another way as the limit as x tends to x naught of f of x minus f of x naught altogether over x minus x naught. So we can actually derive all these formulas here from this one. Okay, we can derive all of them from that. So what we need to do, just set x minus x naught to be equals to h. Or remember your physics practical, where you have x minus x naught to be what? Changing x, Nabi. Good. So if you just set that to be changing x, then you get the remaining two formulas here. So let's say, or x minus x naught to be equals to changing x. So let's say, now, if you replace x minus x naught as h, we will get this, Abi. Now it means that you now make x the subject here, or let me say, yeah, you make x the subject. This one will go to the other side and become x naught plus h. Okay, so x will become x naught plus h. Come on, Abi. So that you have f of x naught plus h, minus f of x naught over h, Abi. Then this one, remember that x is minus x naught, x is x naught plus h, Abi. Aha. So by the time you take x naught to the other side, we have h tends to 0. Okay. So what I mean is x is x naught plus h tends to x naught. So by the time we move this x naught to the other side, you're going to have h tends to 0. So you get this one. So now the value of x naught that you have here now can now be generalized to any point x. So So now this formula is what we want to use to solve to find the derivative, and they call this one derivative from the first principle, meaning that we are making use of the definition of differentiation. So that's what they mean by the derivative from the what? The first principle. Okay. So let's take a function. Suppose f of x equals to 3, let's say equals to, give me x plus 5, for example. Let's start from the simple one. So what we'll do is, we'll look at the formula that we want to use. We want to find this, but we need this, we already have something here that we just need to replace. So what we need is find the value of f of x plus change in x. F of x plus change in x. We already have f of x. So f of x plus change in x will be anywhere we see x in f of x, we replace with what? F of x plus change in x. So that will give us x plus change in x plus 5. Now remember that if you are looking for f of 2, if f of x is defined this way, what you just do is wherever you see x, you replace with 2, abi? So now we are looking for f of x plus change in x. Wherever we see x, we just put x plus change in x. That's it. Are we together? Okay. So now, but they ask us to do something in this numerator. So we will now say that dy dx is equals to the limit as change in x tends to 0, abi? Of what? F of x plus change in x, which we have gotten here, x plus change in x plus 5 minus f of x. Let me enclose this in a bracket so that then that will be x plus 5. Good. Now divided by change in x, abi? Okay. So this is equals to the limit as change in x tends to 0 of, you can open the bracket now. If you open the bracket, you will observe that you have x plus change in x plus 5 minus x minus 5. Look at it. Minus, open the bracket. So this is minus x, then minus 5. Divided by change in x. Now, look at it. We're having x minus x. That goes to 0 now, right? Then here, plus 5 minus 5. That also goes to 0. So we can just see x minus x, then plus 5 minus 5. That goes to 0, right? So what do we have left there? You'll say that we have change limit as change in x tends to 0 of change in x over change in x. And this one will give us what? 1. You have the same value. Divide by the other, okay? 1. So we have the limit as change in x tends to 0 of 1, abi? So what is the limit of a constant? The limit of a constant is still that constant. Yes, the limit of a constant is that constant. So this is just equals to what? 1. Now, I know you are familiar with some elementary standard derivative. If you differentiate this one, what will it give you? Just differentiate, applying that formula directly. That will just give you 1. Abi? Differentiating this constant that you have, that one gives you the 0. So using the formula, I mean, the first principle, we still have 1. Never change anything. So let's take one more example on this. Suppose f of x equals to x squared plus 5. I want to differentiate from the first principle. So all we need to do is, our f of x is x squared plus 5. We need to find f of x plus change in x. Abi? So that means f of x plus change in x will be equal to, wherever we see x in f of x, we now replace with x plus change in x. So mean that we have x plus change in x all squared, all together, then plus 5. So the next thing is we can simplify this before we now substitute into the formula. So we need to expand this. If we expand this, we're going to have this to be equal to x squared, right? Then x times this one, that will give us x plus change in x, right? Then this multiply this, we have x change in x again, then plus change in x squared. Okay, then plus 5. Okay. Now, if you don't get how we have done this to obtain this, so we can do this. We can do this x plus change in x squared is equals to x plus change in x multiplied by x plus change in x. Okay, so let's go back to our primary school. This multiplies this first, and this multiplies this. Then later we multiply this by this, and then multiply this by this. So we have x times x, that is x squared. Then x times change in x plus x change in x. Then this change in x multiplied by x change in x, and change in x multiplied by change in x, that will be plus change in x squared. So if we collect like terms, these are like terms, so we have x squared plus 2x change in x plus change in x squared. So we can replace this. So this will become x squared plus 2x change in x plus change in x squared plus 5. Okay, so now we can now substitute into this formula that dy dx is equals to the limit as change in x tends to 0 of the value of this now is x squared plus 2x change in x, right, plus change in x squared plus 5 minus x squared plus 5, right, in a bracket. But you don't forget that this minus will affect the two of them, so that we're going to have minus x squared minus 5. Is it clear? Okay, so divided by change in x. So here we have x squared and we have minus x squared, that goes to 0. Then plus 5 minus 5 we also go to 0. Good. So what do we have left? We have the limit change in x tends to 0 of 2x change in x plus squared over change in x. Okay, now this is equal to the limit change in x tends to 0 of, if you look at the numerator, something is common. What's common? Change in x is common. Okay, we factor that out. What do you have left for the first time? For this first time, okay, we have 2x plus, what do you have left? We have two of it. One is, okay, we have change in x divided by change in x. Now change in x, we take care of this change in x, and what we have left is the limit as change in x tends to 0 of what? 2x plus change in x. Now we now substitute 0 for change in x. Look at this, change in x tends to 0. So from our definition of limit, so wherever we see change in x, we replace with 0. Now that we want to substitute, we observe that I did not write anything like limit again. So we just have plus 0, and this is equal to what? 2x.